So today we're going to be talking more about probability, but we're going to start talking about a particular type of probability, which is a discrete random variable. So essentially, random variables are just the name we give to these outcomes from probability distributions. So it's what we've been talking about, but now we're actually giving it a name. So a random variable is a numerical value associated with each outcome of a probability distribution. So we call our random variables, we just give them some name. The most common one we're going to use is X. In the next chapter, or in the next section, you're going to see me using R for binomial random variables. We use R, X, T, Z, X bar. So we actually use the mean as a random variable also. So these are the main ones we're going to talk about in this class. But just know all these are names, right? So this X is just a name for whatever our random variable is. So for example, X might be the number of sales calls a salesperson makes in one day, or the number of hours spent in calls on one day. So those are our random variables. They're just names given to the things that we're doing that we want to look at the probability of. So the number of odd numbers you get when you roll a dice 3 times. The number of heads tossing a coin 1,000 times, right? Those are random variables. So they're just what we're looking at from our experiments that we're talking about. So continuous, we're measuring things, right? So we have an uncountable number of possible outcomes represented by an interval on the number line, right? So for example, the hours spent in sales calls in a day is going to be continuous, right? Because you could spend 2.5 hours on a call, or 3 3/4 of an hour on a call, right? So you can have parts of something. You're measuring the number of hours. So continuous random variable, remember, we are measuring something. Now the ones we're going to be focusing on in this chapter are going to be the other type of random variable, which are discrete random variables. So we're going to spend some time with continuous random variables later in the semester. But for now, we're going to talk a little bit about discrete random variables. So remember, discrete, what are we doing? So if we're measuring with continuous random variables, what are we doing with discrete? We're counting them, right? So we're counting something. In this case, we're counting the number of outcomes that we can list. So our random variable might be the number of sales calls a salesperson makes, right? You can't make half of a sales call. So remember with this, no partial pieces, right? So no partial results, no fractions, no decimals for the actual number of outcomes. So number of heads on 50 coin tosses, right? You can't get 20.5 heads, right? It's not going to happen. So these, you're counting, and so it can only take on finite discrete values. And so that's why we call it the discrete random variable. And these two slides should look very familiar because these slides were in Chapter 1's PowerPoint too. All right? So this is the same exact slides I gave you way back then. So you tell me, is this random variable X going to be discrete or continuous? So X is the number of Fortune 500 companies that lost money in the previous year. Discrete, right? Because we're counting. How about this one? The volume of gas in a 21-gallon tank. Continuous. Why? Exactly. You could have 5.5 gallons of gas in your tank, right? And it'd be okay. Might have to go to the gas station, but it'd be okay. All right. So put continuous out of your head for a little bit. We're going to come back to continuous in Chapter 6. And continuous is going to be where we are for the majority of the rest of the semester. But for now, we're just going to focus on discrete, and we're going to be talking about a discrete probability distribution. So what a discrete probability distribution is is basically a table of every single possible outcome. So remember, we have a finite countable number of outcomes, right? So what that means is we can list out every single outcome that we could get. So if you're tossing a coin 50 times, for example, and you want to record the number of heads, you could list out every single possible number of heads that you could have tossing that coin 50 times, right? Right? You could list that out. So that's what a discrete probability distribution is it's literally a listing of every single possible outcome along with its probability. So it's all the outcomes or all the possible values it could take on together with the probability of that outcome occurring. So essentially, it's a table of probability values. And so, of course, it has to have these conditions, both of which should not surprise you, right? Because we've talked about them before. So the first one, every single probability has to be between 0 and 1, right? We've already talked about that. All probabilities, no matter what, have to be between 0 and 1. And then similarly, the sum of all the probabilities has to add up to 1. Because if they're all between 0 and 1, when you add them up, you've got to add up to 1 whole. So the sum has to be 1, and the probability of each value itself has to be between 0 and 1. So something you might see on a test relating to this. I might give you some tables and ask you, tell me, are these valid probability distributions or not? So what should you look for? You should look for probabilities individually that are not between 0 and 1. So a negative probability, for example, or a probability bigger than 1, but really negatives. Look for a negative. Look for something bigger than 1. And then look to make sure they all add up to 1. So you have to meet these two criteria to have a valid probability distribution. All right, so these are just literally the steps to building the probability distribution. You don't need to really memorize these steps. Basically, all these steps say is you make a frequency table. You make a frequency table. So you list out all the possible outcomes, find the probability of each outcome, right? So really what this is saying, you're finding the relative frequency. That's what these 3 steps really tell you. You're finding the relative frequency. And then checking that it's between 0 and 1. So all a probability distribution is a relative frequency table. So what we did back in chapter 3, that's all we're doing now. It's a relative frequency table. So let's say, for example, we've got an industrial psychologist who administered a personality inventory test for passive-aggressive traits to 150 employees. So they were given a score from 1 to 5. 1's extremely passive, 5 is extremely aggressive, and 3 indicated neither trait. So let's construct a probability distribution for this random variable. And then we'll draw a histogram of it just because it's a good review. Again, I'm trying to give you some review stuff as we're starting to progress closer and closer to May. So to build this probability distribution, right, all you have to do, if you know how to make a frequency table from chapter 3, then you know how to build this probability distribution. So all you need in a basic probability distribution, at its most basic, are the x values. So the x values are just what your variable could take on. In this case, you could only get a 1, 2, 3, 4, or 5 on that test, right? So what you can take on and its probability. So probability is just another way of saying what? That's frequency over n, right? So it's the same thing we did in chapter 3. We're just labeling it a little differently now. Instead of saying this is relative frequency, we're now just saying this is the relative frequency probability or probability of x. So you tell me, how would I calculate my probability for a score of 1? 24 over 150, exactly. And so then whenever we do that as a decimal, what do you get? 0.1 what? Yes. All right. Same idea all the way down, right? So 2 would be 33 out of 150. 3 would be 42 out of 150, and so on, right? So we get 0.16, 0.22, 0.28, 0.20, and 0.14 whenever we write these out as decimals. All right, everyone still with me? That really is all a probability distribution is at its most simplest. Now, how do we know if this is a valid probability distribution? Add them, so check each one first. Are they all between 0 and 1? So they're all between 0 and 1, so it meets that check mark. So then the last thing to do to make sure, just find the sum of the probabilities, add them all up. So 0.16 plus 0.22 plus 0.28 plus 0.20 plus 0.14, what do you get? You get 1, right? Better be 1 or very close to 1, right? Just like relative frequencies when you're adding them up, because it is relative frequencies, right? We're just calling it something different. So it better add up to 1 or very close to 1 if you're using the decimals, right? If it rounds close to 1, so something like 0.998 or 1.001, that's fine as long as it's close enough to 1. All right. How would we do the histogram now? So what goes along my x-axis for my histograms? So remember, we want to use the boundaries down here, right? So we just make all of these minus 0.5 for the lower one, plus 0.5 for the upper one, right? So we end up with 0.5 to 1.5 for my class of 1, right? So my middle value. And then 1.5 to 2.5, 2.5 to 3.5, 3.5 to 4.5, 4.5 to 5.5, so that our bars are touching in the same width, right? So if you've forgotten how to do that, go back, look at it in your notes from earlier in the semester. And so then our frequency, let's do relative frequency instead. Let's make a relative frequency histogram. Shape's the same. The only difference is we're using the decimals we got instead of the whole numbers. So I'm going to go up by 0.05s. All right. And so got my relative frequencies along here. I've got my scores down here. So the score of 1, which is our class from 0.5 to 1.5, has a relative frequency or probability of 0.16. And then we've got 0.22, 0.28, 0.20, and 0.14. And our title, right? If you're a little fuzzy, forgot what goes where on the histogram, right? What you have to have with it, go back, review that, because I guarantee you'll see it again. All right, so with any distribution or any variable, what two pieces are important for us to know? What do we always want to know? What two statistics in particular do we use all the time? So mean and standard deviation. The two big ones I said we're going to use in every single distribution, right? So for a discrete probability distribution, now it's important to know, since this is discrete, we know the population, right? So because we have a discrete random variable, we have the entire population. We know every single value it can take on. We can find the probability of every single value it can take on. So these will always be parameters. So we can find the population mean mu and the population standard deviation sigma in a minute. So to find the population mean mu of our discrete random variable, it is the sum of x times the probability of x. So following order of operations, what are you going to do here first? Are you going to find the sum of x's first and then multiply the probability? Or are you going to do x times the probability and then add them all up? What do you think? So what's order of operations tell us? Got to multiply first, right? So we're going to find x times p of x and then add them all up. So you can really think of this as if there's an understood parentheses here, as if this is the sum of x times p of x. All right. So really what we're doing here, so the formula is a little bit different, right? It's the same math we did in chapter 3. It just looks a little bit different because we're writing it in a different form. So to show you that it's the same math, we're going to find the mean and standard deviation of this data set. So let's think what you would have done in chapter 3, right? So thinking back to chapter 3, what was our formula for population mean? It's the sum of x over n, right? So what would that mean here? What would this data set really look like now? So we've got the frequency table, right, where we've grouped everything together. But if you had to actually find that mean using the technique from chapter 3, what would you have to do? You would have a data set with 24 ones in it, right? So 1, 1, 1, 1, 1, 1, 1, 24 times. So you would have to literally sit there and do 1 plus 1 plus 1 plus 1 plus so on all 24 times. And then plus 2 plus 2 plus 2 plus 2, 33 times. 3 plus 3 plus 3 plus 3, 42 times. So on all the way through that entire data set, right? Until you had all 150 of the data values added together and then divide by 150. That's what you would have done, right? So now, here's where that new format comes in. If you think about this as mu being the sum of x times p of x, right? Well, let's think, what is this doing here? So what are we doing? So in this case, this is 1 times the probability of 1, right? So 1 times, and I'm going to write it in the fractional form, 1 times 24 over 150. Plus 2 times 33 over 150. Plus, and so on for 3, 4, and 5, right? So if we think about this, what are we really saying here? What is repeated addition the same thing as? That's multiplication, right? So by saying we're going to add 1 to itself 24 times, all we're really saying is 1 times 24, right? And then 2 times 33 is the same thing as 2 plus 2 plus 2 plus 2, 33 times. So all we're doing here, we're condensing that repeated addition into the multiplication. And then dividing them by the 150 in our probability, well, if we have, so we're going to have all these fractions over 150, right? And so, well, that means we can rewrite them as this. Notice the same math, right? It's the exact same math as what you would do if you did it in chapter 3. It just looks a little bit different. So I will give you, to help you out with this a little bit, I will give you a table to lay it out. So I'll give you the same layout. So just like I did with standard deviation in chapter 3, I'm going to give you the table to help you walk through finding mean and standard deviation. So you'll have a table. It'll have the x's in it. May or may not have the probability. If I give you the frequency, I won't give you the probability, vice versa. But you'll have something to either find the probability or you'll have the probability in the table. And then you'll have a column for x, p of x. So you'll have all that given to you. So in this case, if we work through the table, right? So x times p of x, 1 times 0.16 is 0.16. 2 times 0.22, 0.44. And so on through the table, right? So 3 times 0.28, which is 0.584. 4 times 0.20, which is 0.80. And 5 times 0.14, which is 0.70. And so from there, what do we do to find our mean? You add up this column, right? So our mean is literally the sum of this column. So the sum of xp of x. So it is 0.16 plus 0.44 plus 0.84 plus 0.80 plus 0.70. And so we add all that up and you get the mean. So what do we get for our mean in this case? 2.94, good. So variance, again, the formula looks a little bit different for variance and standard deviation. I'm going to, just like before, focus on variance, because once you get variance, the same thing is always true as has been true. Standard deviation is the square root of variance. Doesn't matter. That's just square root of that. So variance in this case, sum of all of this stuff. So the sum of the data value minus the mean squared times p of x. So again, it looks a little bit different, right? So we've got that. So we've got the deviation squared, but now we're multiplying by the probability of that happening. So all that's accounting for, it's basically the same idea as what we did here, right? Multiplying by the probability, we're accounting for that repeated multiplication, so that repeated addition for every single time that data value occurs. And we're also dividing by n in this case, right? Since it's a population. So divide by n. So that's what multiplying by that probability does. We're accounting for the repeated addition, and then, so for every single data value, and then dividing by our population size, or number of data values. Otherwise, it's the same idea. So just like before, I will give you the table to help you work through this. So you'll have the table to work through our variance, through your variance. So you will have something laid out exactly like this. So let's now, same data set. So the way I'll give it to you, you'll have a column for x, you'll have a column for p of x. You'll have the column that I already gave you that we used to find our mean, x p of x. I just took it out for space on this one. So you'll have all those columns, and then you'll have these other three columns. So data value minus mean squared. Those two come straight from the last chapter 3 table, right? And then the new column, the deviation squared times our probability of x. And it's just the tedious process of filling in that table, right? To find our standard deviation and variance. So that process, so we got our mean was 2.94. So now, just like before, right? Same exact thing we did in chapter 3. Data value minus mean, right? Now, here's where you have to be careful. One of the big mistakes I see students make all the time on this, they will not pay attention to which column they're subtracting. And so they'll subtract the probability, the mean from the probability, instead of the probability, the mean from the data value. So be careful. Make sure you're subtracting from the right column, in this case, the first column, x. So this one should be 1 minus 2.94, which gives you what? Mm-hmm. Exactly. And then same thing, 2 minus 2.94, which gives you negative 0.94. 3 minus 2.94, which is 0.06. 4 minus 2.94, which is 1.06. And 5 minus 2.94, 2.06. For these standard deviation and variances, you don't need to worry about adding up these two columns. I know we did on the chapter 3 one to see if the distribution was roughly symmetric. It's going to be rare for our discrete random variables to be symmetric, so there's no real point in adding up this column here. It's just going to tell you, hey, it's not symmetric. It's skewed to one way or the other. And then this does not give, well, it technically gives you the sum of squares again, but we don't need the sum of squares for this calculation since well, actually, it doesn't even really give you the sum of squares because it's not even accounting into the frequencies. So it really doesn't mean anything like it does with our regular formula for variance and standard deviation. So really, it's just working through all the way until you get through this last column. So next column, same thing, right? So negative 1.94 quantity squared. And remember, when you're putting this in your calculator, parentheses around it, especially if it's negative, right, to make sure that you get that positive number out. So all of these should be positive. So 3.7636. And notice I'm keeping more decimal places here, right? Why am I keeping so many decimals? At the end, I'm going to want to round it, right? And so it's better to have more decimal places throughout so that you can then round at the end and get a better answer. So usually I recommend around 4 in the table because normally we're going to round to probably 2 at the end. So it's a good idea to keep 4 if you can. So negative 0.94 squared, we get 0.836. And so on down the line. So keep squaring each of these numbers. Until you get all of them squared. Last step, you're just multiplying this number that we got in this column, right? So in this case, 3.7636 times the probability. So now is where you're going back and using this second column. So 3.7636 times 0.16, which gives us 0.602. And then same thing all the way down. So 8836 times 0.22 gives you 0.194. Notice I'm down. I went from 4 decimal places here, kept 4 when I squared it so I'd have more accuracy. And now I'm rounding to 3 because in the end I'm going to round to 2. Actually, I'll end up rounding, we'll see, 2 or 3. So we keep on doing that. So 0.0036 times 0.28, and we get 0.001. 1.126 times 0.20, 0.225, and 4.236 times 0.14, which gives you 0.594. All right. So we've got our table built, right? Well, the last step to find the variance is a lot easier after you've done the tediousness of this table. The variance is easier than it was before because there's really nothing else you have to do to get the variance other than add up this last column. So your variance is the sum of this column. So before, where the sum of your last column of the table was your sum of squares, now the sum of your last column is your variance. You don't have to do anything else to get the variance. So add up this last column, and that is your variance. So if we add up 0.602, 0.194, 0.001, 0.225, and 0.594, you should get, or somebody tell me, what do you get for that one? So that is your variance. So your variance is 1.616. And then, of course, how do we get standard deviation from that? Square root it, right? So standard deviation is just square root of 1.616, which is approximately what? Give it to me to one decimal place. 1.3. Good. Questions? So really, this process is more tedious than anything else in terms of filling out the table, right? It's just a long and tedious process to get to that answer. But the actual math itself in here, none of it's really difficult, right? It's just subtracting, squaring, and multiplying to get to it. All right, so the last thing I want to talk about in this section is expected value. So expected value is just another name for the mean. So expected value is just another name for the mean. But what we really talk about when we're really talking about expected value, what we're really saying is in the long scope of things. So if everything keeps the same pattern, what do you expect a typical data value to look like, right? That's why we call it expected value, is what do you expect to happen in the long run, in the long scheme, what's an average value going to look like? So that's what our expected value is. So expected value is nothing but the mean. Where this is really useful is predicting gains and losses with money, for example. So insurance companies, they might look at what is the expected value for the amount of claims they're going to have to pay out on in a year, right? Or the expected value of how that you're going to get into a car accident. An insurance company is going to look at that. Or maybe you want to know, if you buy a lottery ticket, how much money should you expect to win? Give you a hint. You don't win. The house always wins, as we're going to see in a second. So to that, let's say there's a raffle where 1,500 tickets are sold, and they sell the tickets for $2 each, and there are 4 prizes: $500, $250, $150, and $75. So what do you think? Who's going to win here? Whoever's doing the fundraiser, selling the raffle tickets, or you? So let's find out. What is your expected value of gain? How much money do you expect to win in the end? So what should you expect to happen? So to figure this out, well, we need to know what our X values are. So what are our possible gains, right? So how much money could you win? And then the probability of it. So what are the possible gains you could have? So how much money could you actually win? Okay, so if you win the prize of $75, how much money do you actually gain, though? You lost the $2 you paid in for the ticket, right? So it's actually a gain of $73, right? So you could have a gain of $73. What else could you gain? $148. What else? $248. $498. Is that it? -$2, right? You could also gain -$2. You could just lose your money that you paid in for the ticket. That's the one people like to forget about, right? Same idea when you go buy a scratch-off ticket. If you don't win, you forget that you had to pay the $2 for the ticket, or the $1 for the ticket, or the $20 for the ticket, whatever ticket you're buying, right? People tend to forget about that one. So what's the probability that you're going to win or gain $73? You got a 1 in 1,500 chance of winning $73 or gaining $73, which is winning $75. Good. You've got a 1 in 1,500 chance of gaining $148, a 1 in 1,500 chance of gaining $248, and a 1 in 1,500 chance of gaining $498. What's the probability you're going to lose $2? 1,496 out of 1,500, right? So just looking at that, what do you think is going to happen with your expected value? It's probably going to be a negative something, right? You're probably going to lose money when you buy a raffle ticket. Let's be realistic. Your chances of winning are not likely, right? So then we multiply, so 73 times 1 over 1,500. So 148 times 1 out of 1,500. And we calculate all of these numbers. 248 times 1 out of 1,500. 498 times 1 out of 1,500. And negative 2 times 1,496 out of 1,500. And so then we do all that multiplication, and we add all of this up, and what do you get for our expected value? So you should end up getting negative 1.35. So what does this mean then? So now we've got our mean, we've got our expected value. So let's translate that. What does that mean? So in this case, what this means is in the long run, you should expect you're going to lose $1.35 if you keep buying raffle tickets. So for every raffle ticket you pay $2 for, you should expect you're going to lose $1.35 of that in the long run, right? So if you keep buying raffle tickets and keep buying the raffle tickets in this raffle, you should expect you're going to lose $1.35 for every $2 you spend. So you're losing money. All right. So expected value is really beneficial to tell you what's going to happen in the long run. In the long run, you're going to lose money on every single ticket you buy. That's what the expected value tells you. So this week for your hybrid assignment, you're going to look at the probabilities of winning in roulette. Anyone ever played roulette or seen somebody play roulette? So the wheel, okay, so the wheel where you spin it around, they spin the ball around the wheel, and wherever it stops, you've placed your bet on either a color or a number combination. So this week's hybrid assignment, you're going to look at those probabilities, and based on the usual payouts in Vegas, what your chances of winning are. So what your expected value would be for placing a $1 bet or placing a $5 bet or placing a $10 bet. That's what you're going to look at in your hybrid assignment this week and see, is it really worth it to play roulette? And which type of bet gives you better chance of maybe winning some money?